Welcome to the Austin Forum Upload, the podcast of the Austin Forum on Technology and Society. I'm Jay Boisseau, the Executive Director and founder of the Austin Forum on Technology and Society. And this week's topic is quantum computing. I'm here today with two longtime friends and colleagues, Bob Sorensen, the Chief Quantum Computing Analyst from Hyperion Research, and Rima Alameddine, the Chief Revenue Officer for IonQ. Thanks for joining us, guys.
Hi, Jay. Happy to be here. Looking forward to the conversation.
Same here. It's a pleasure being here. Thank you.
Yeah, it's great to have you both here now for a couple of reasons. One, quantum computing has really been in the news a lot lately, and more people are hearing about it, not necessarily understanding it yet, but hearing about it, and that's the first step. The Austin Forum on Technology and Society has a big event on September 5th that will be in person and live streamed globally. And so we're looking forward to a huge global audience for that event. But I felt like it was great to get with you two today and set the stage for people with a quick overview of what quantum is, so that as we dig into this more in the Austin Forum programming, people will hear things a few times and some of the rather complicated points will begin to sink in. So thanks for being here. And I'm going to launch right into the interview in a second. But first, I'd like each of you just to introduce yourself and share a little bit about what you do in quantum computing. Rima, how about we start with you?
I'm the Chief Revenue Officer at IonQ. What that means is I'm responsible for IonQ's go-to-market and revenue at the company. And we believe that quantum will have the same trajectory that AI had, but it will be exponentially more powerful and disruptive.
Great. Thanks, Rima. And Bob, as an analyst tracking the quantum computing market, tell us a little bit about yourself and what you do.
Yeah, hi, I'm Bob Sorensen. As Jay said, I'm the Chief Analyst for Quantum Computing here at Hyperion. And just tell you a little bit about Hyperion, not as a commercial, but more as a background, a perspective where we come from. We track HPC. We track advanced computing in whatever form it may be. 15 years ago, we'd be looking at what Cray Research was producing for modeling and sim. Then along come things like big data. Along came things like HPC in the cloud. You have the AI explosion powered by things like NVIDIA GPUs and such. So we look at the pointy end of the spear when it comes to advanced computing. And so in some sense, we don't look at quantum as a standalone thing. We look at quantum as another tool in the toolbox for end users to address their most vexing and critical computational requirements. So we see quantum as it's an accelerator. It's a way to continue the trajectory that has been the proud tradition of HPC, which is performance doubles every year or so. And people are looking at quantum to help assist in that trajectory going forward for the next decade and beyond.
Bob, I'm glad you brought that up. All of us at some level have a high performance computing background. And when people talk about quantum computing, I always remind them high performance computing is just that. It's whatever we can do to get higher performance than mainstream computing. And quantum computing is one of those directions that may give us much greater performance. Of course, as we all know, it might be integrated with classical HPC, and maybe we'll talk about that a little bit here as well. But first, I want to ask the first question. When you talk to your friends and outside of the quantum computing space, most of them probably don't understand what quantum computing is. Fortunately, most of them have probably heard of it, at least in the last year, but probably don't understand what it is. How do you, in a big picture way, tell them what quantum computing is and convince them that it really is something real, even though it sounds like something out of a Marvel movie or something?
Well, I'll jump in first. Sorry. The bottom line here is what I like to tell people is, look, you wouldn't really know it when you look at a computer that you sit at your desk and you download reels off of Instagram or something. But that's all ones and zeros. And you do an awful lot with ones and zeros, but at some level you're limited. So I like to say, the world we live in is 1 and 0. The quantum space, just think of it as it's a big circle. And instead of being limited to a 1 and 0, you can live anywhere on the outside of that circle, anywhere on the sphere to represent a single data point. So you're really moving, in some sense, at its most simple, from a 2-dimensional, almost a 1-dimensional binary 1 or 0, up to a 3-dimensional model. And think of all the extra capability you can have, all the innovation that comes from being able to compute not by 1 and 0, but on a giant sphere. And and all physics aside, that's really what quantum is. It gives you more opportunity to do more compute, more innovation within kind of the same floor space. And that's a good thing to have.
I couldn't have said it better, but I'll just try and fill in a few more aspects that could be helpful. So Bob explained it at a high level. I'm going to just take it one step down and say quantum computing actually leverages the principles of quantum mechanics at the subatomic level. And what it does is, like Bob said, classical computing uses zeros and ones, while quantum computing uses something called qubits. And this is very different than how we actually operate in the classical fashion, because it uses something called superposition, where a qubit can be in two states at the same time. So it could be in a 0 and a 1 state at the same time. And it also uses another feature of physics at the subatomic level, which is called entanglement. And what that means is that two different atoms are actually mechanically entangled, even though they're at a distance. And these are that both superposition and entanglement are capabilities that are not available on classical computers. So now we're using features and capabilities that do not have a parallel on a classical system, and we're able to do things that are not possible otherwise. And it actually allows us to have exponential speed ups and to address things that you cannot address in a classical way. And that, the promise is that we're going to unlock new possibilities and actually get to things that are interactable today.
I love both of those explanations. Yeah. I've used variants of each of those and explaining it to friends of mine. The only thing that I would probably add that is, I remind my friends that, if you have 32-bit processor, you can calculate a 32-bit result. If you have a 64-bit one, you can calculate two 32-bit results. So, or 164. So it doubles with the number of bits, whereas in quantum, because of the very things Rima just said, entanglement in particular, on top of superposition, you get many more possible calculational states in the same amount of time. So it's inherently highly parallel, as opposed to having to scale it out parallel. So the potential is just enormous. And I remind folks who say, well, this sounds a little like magic, how do we know it'll work? And I remind them that, well, classical computing leverages the principles of physics at the atomic and molecular scale for semiconductors and electron flow and et cetera. And we're just leveraging the quantum mechanical physical principles of these subatomic particles, a different, harder to manipulate, but a different, but absolutely experimentally proven true set of physics. So, but because it's at a different scale and a different set of physics, the engineering is a lot harder, but we'll get into that.
So I was just going to add one thing to what Jay said, because you're right. If there's 64 bits on a classical computer, you can represent one of 2 to the power 64 states. But on a quantum computer, you can represent 2 to the power 64 states at the same time. And that is like 18 quintillion states at the same time, which is mind-boggling to even think about.
The only thing I'd add to that is while we may be now denigrating to some extent the binary world, when we talk about classical, you have to remember, we all think in the classical world. We live in the classical world. Right. We are quantum phenomena, things like superposition and entanglement, this spooky attractions at a distance. That's not intuitively obvious. That is an entirely different way of thinking. That is very different from the visible world we live in, which is why, and sometimes it seems very confusing, and why it's so hard to get a handle on what quantum really is, because it requires, in some sense, an entirely different way from actually how our brain is wired. So it's not that anyone who doesn't know the field is missing something. It's that the field at this point right now is really quite mystifying and beyond what we can understand from an observable perspective. So I don't understand quantum as well as some people do. And I don't think most people understand quantum perhaps as well as they think they do, because it's so different from our classical world that we live in and how our brains evolved from.
Yeah, that's when I try to explain quantum computing in terms of quantum physics to my friends, the quantum physics is the part that trips them up, because as you said, what happens at the quantum level physically is very different than our classical daytime living experiences. Mm-hmm. So I say, look, you don't know how a microprocessor works. This, of course, being to my non-computing friends,
Right.
say, you don't know how the microprocessor works. Trust me, it works on atomic scale physics and such. This does too, but it's just some different physics at that scale that make it much faster if we can harness it well. And then they're like, okay, I think I'll just trust you.
Exactly.
So I hope
Yep.
we get to a point where these quantum computing systems are proven and reliable, and people are trusting the answers they generate. Speaking of which, and using them, what are one or two big problems that each of you think are attractive candidates for this much computational performance? What are the drivers? Why do we need quantum computers? Why can't we just keep building classical computers that, advance with Moore's law and they get a little bit faster, and then hooking more of them together into parallel clusters? So maybe I've kind of asked you two questions in one, but what are some drivers, and why can we not solve that with classical high performance computing systems?
We're reaching a number of endpoints when it comes to the trajectory of advanced computing. I talked earlier about 40 years of performance gains. We're reaching some ends of. It's getting more and more difficult to pack billions upon billions of transistors onto a single chip. It's very expensive. It takes a long time to design. And increasingly what we're seeing is supply chain issues. There's only one or two companies in the world capable of producing the equipment to build the chips that we use in some of these machines. So complexity of the chips itself is a problem. When you pack all these chips together, you have power concerns. Now you have to cool them. So you can have machines that generate huge quantities of power. People are now thinking about ways to run liquids very aggressively through machines to cool them. That's another limiting factor. The idea of cost nowadays, a great example is Department of Energy now has a trajectory to build 3 of the most powerful HPCs in the world. Each machine's going to cost DOE about $600 million a piece to build that. That's out of the range of most commercial corporations by orders of magnitude.
Mm-hmm.
What's more pernicious about this is those big machines are in the one going into Argonne National Labs, targeted for 60 megawatts of power. We're talking large neighborhood size of power consumption, which means in addition to a $600 million paycheck to buy that system, they may be looking at $300 million of energy cost to power that system over, say, its 5-year lifespan. 60 megawatts of power in an age where more and more people are concerned about renewable, sustainable, and eco-friendly power consumption means these big machines simply cannot continue on the path they're going. We can't have billion-dollar exascale systems consuming hundreds of megawatts of power, available in some sense only to a very small class of users. So everyone is looking for the next big thing. What's the next accelerator that we can bring to the quantum computer, to the classical computing world, that can keep the trajectory going without having to deal with power, complexity of manufacturing, and perhaps most importantly, cost? So those are the things that are driving any search for new technology. And right now, quantum is probably the most promising candidate to meet those requirements.
To your point, HPC, has served us so well for so many years, but it has limitations. And the limitations are because it uses classical physics. And so it cannot efficiently address problems that require quantum level computations or deal with exponentially complex problems. And just to give you an example, our quantum computer runs on wall power. And we right now are at 29 useful qubits. That computer actually can do 2 to the power 64 states. It can examine them at the same time. And that starts rivaling supercomputing. And when you start thinking about putting a quantum computer and using just wall power versus using $300 million just for power and cooling, like you were just saying. This is why you start thinking, you know what, we need a different kind of computer to address these really big, complex problems. And just to add to that, quantum computing is not good for everything. Quantum computing will not replace classical computing, but for those specific problems that need that kind of compute and need to examine all these different states very fast, and the first question you asked, actually, Jay, was what are some of these kinds of problems that where you need quantum computing. It's things like optimization, like route optimization, supply chain management, portfolio optimization. These are problems that are actually very difficult on a classical machine. And the reason they're difficult is they take a lot of time and resources. And as the quantum computers become larger, we're hopeful that we are actually going to be able to come up with new breakthroughs in drug discovery, material science, and actually climate modeling. That's where we need to simulate very complex interactions between various atmospheric and oceanic variables, and those require computational power that is immense and is too complex for today's classical machines. So that's where we want to look at quantum. We don't want to leverage quantum for things that we could do today on a classical system.
You guys hit some great points there, and I'm going to try to summarize these for our listeners. We have ridden Moore's law to more powerful processors, and then we use high performance computing to aggregate those processors. And so we've been able to build bigger and bigger classical high performance computing systems or supercomputers. But as Bob said, we're running out of headway. Moore's law is slowing down. It's harder and harder to see how we're going to make these processors faster. Meanwhile, we're using more and more power, and these systems are thus this brute force classical computing approach. It delivers some fantastic supercomputers, but they're getting incredibly expensive and using lots and lots of power. Both of you in the opening talked about how the quantum nature of these materials, if you can manipulate these qubits, can allow you to do many more computations at once, as opposed to this brute force scaling. And so even small qubit count systems can do certain problems faster than very, very large classical computing systems. Rima, you gave a couple of examples. The only thing after this little summary I gave that I'm going to add to it is that one of the first people to propose quantum computing systems was Professor Richard Feynman back in the 80s. And he did it not even for the optimization problems that could get very huge, but because nature itself is quantum mechanical. Chemistry at the lowest level is quantum mechanical and obeys quantum physics laws as well as some approximations we can make. But to do exact quantum chemistry requires a quantum computer. So to me, that's actually going to be the most exciting thing, when we can really design new pharmaceuticals based on truly accurately simulating the full quantum nature of materials instead of trying to approximate it on these incredibly large, power-hungry, approximating classical systems. So very exciting future, I think, there. Let's talk about the nature of these quantum computing systems a little bit now. Rima, you work with one company that develops a certain kind of quantum computer. Our audience probably thinks in terms of computers are all kind of the same. Maybe it has an Intel processor or an AMD processor or an ARM processor. Maybe a GPU has been added, a NVIDIA or AMD GPU, but they're familiar with the concept of these silicon wafers and etching and putting transistors down on it. And to first order all these classical computing systems all leverage, as Bob referenced earlier, the same small number of companies and same basic approaches. But that's not true in quantum computing, right? Why don't both of you share how different companies are trying to make qubits in very different ways?
I could share what IonQ is doing. So IonQ is the world leader in quantum computing. We have the best commercial systems in the industry. And like we said, like actually Jay was saying, there are many different approaches to quantum computing. There's superconducting, there's ion trap, there's natural atoms, and they all have strengths and weaknesses. So we actually at IonQ, we use trapped ions as qubits. And the reason we do that is because they are naturally perfect. We don't need to manufacture the qubits. In superconducting, you manufacture the qubits. And so a lot of the work is going into manufacturing great qubits. For us, the qubits are naturally perfect because they have been used, and they've been used in atomic clocks for years. So what we are working on perfecting is the control systems to trap these ions and to get them to interact with each other. depending on the modality you're using, you're working on perfecting different areas of your technology. We are showing value today in a variety of use cases, such as object detection. For example, we're working with Hyundai on self-driving cars. We're working also with Fidelity and GE on multivariant ML to generate faster and results and predict rare events that cannot be predicted on classical machines. Even with these small problems, we are able to show that we're predicting things that you cannot predict on a classical machine. We're also working on logistics problems and optimization problems with Airbus. So the problems we're working on are small, but the algorithms we're building will be able to scale. So for example, when we take the problem that we've solved for a smaller problem, like maybe we're doing object detection on a smaller picture, but that same algorithm, we can put it on a bigger computer once we have the larger computers, and we'll be able to do bigger things. So this is why we believe the time to actually build these algorithms is now, even though the problems you can actually tackle right now are smaller.
Bob, you want to share, as you look at the whole market, you want to share some of the other approaches that different companies are using to try to harness the properties of electrons and photons and neutral atoms and ions and other things?
Yeah, sure. I mean, you can summarize this stuff, and Rima did a good job, and I like her emphasis about how she talked a little bit about technology and then moved on to end use, because that's kind of a reoccurring theme that we explore here at Hyperion. There are a number of, we call them modalities, and these are different ways that you can establish the quantum phenomena you need to do the quantum calculations at hand. And what's fascinating to me is there are so many different ways to establish that quantum phenomena. There's the superconducting, the IBM and the Rigettis. There's the trapped ions, which is why the company's called IonQ, in case that you think that's an acronym or a trivia question. Then you have things like neutral atoms. You have spin electrons. You have things that are done entirely in photons using light. So there are, in fact, I think at last count, I counted 10 or 12 different modalities, if you will. And the interesting thing is, if I just look at the vendors that are researching those modalities, I found 44 different companies that are involved in doing this. And what's fascinating to me is that has to span 17 different countries. This is not a US only technology.
Right.
The key here is leadership in classical IT, which is something the United States has enjoyed since its inception, does not transfer over to leadership in quantum technology. This is a green field, and different nations around the world are saying, this is our opportunity to take a leadership position. If you look at what's going on in the EU, as well as EU member nations individually, the UK, Japan, China, India, Finland is doing a great job. The Netherlands is knocking it out of the park. Canada, Australia, there's so much interesting work going on there, and so much of it is diverse, and so much of it brings interesting things to the table. So when people call me up and say, oh, I just read about this particular development, so which modality wins? And my answer is, doesn't matter. The winner will not come from a wonderfully designed qubit, or even perhaps from a wonderfully designed quantum processor. It's going to be the organizations that can build on that hardware capability to offer the applications, the algorithms, and the end use cases that matter to HPC end users. So we did a survey last year, and we went out and talked to 300 different quantum computing early adopters, and we asked what their vendor selection criteria was. And things like modality and qubit counts and benchmarks like T1, T2 times all the quantum stuff that appeal to us techno guys, they were interested in demonstrated use case performance, ease with integrating quantum into our existing computational environment, and my personal favorite, demonstrated return on investment. That's what gets the checkbooks out. It's not things like qubit count. It's how can you accelerate my existing applications, and perhaps more important, what new end uses can quantum bring to my company, my organization, that basically drives new lines of research and fosters innovation at every level. So yeah, modalities are cool. They're fun to look at. There's going to be winners. There's going to be losers. There's going to be consolidation. But what's really matters, and Rima hit it right on the head there, it's It's what you do with those systems that's going to determine the winners and losers in the next decade.
Great answers, guys. Thanks for sharing that. I want to follow up a little bit here. So our listeners have heard that there's a lot of different modalities that people are looking at to explore different subatomic particles and trying to manipulate those into qubits and reliable quantum systems. What are the bottlenecks now? It's simply engineering at this point, right? The physics is generally understood, but the engineering of keeping these qubits coherent and entangled, is that the major problem? And what are the other problems that these quantum computing companies are trying to solve?
So actually, not every modality is different. Some still need physics breakthroughs, others don't. It depends what you're doing. In our case, we actually have the physics figured out because, like I said, we use naturally perfect atoms that are perfect in nature. We are working on the engineering challenges, but not all modalities are in that camp. We actually use something called algorithmic qubits to measure the performance of our systems. And what algorithmic qubits are, it measures how the qubits are performing based on some key applications. Actually, QEDC was the first to pioneer that in terms of looking at a bunch of applications and figuring out how the quantum computer is performing. And to what Bob said, Bob, you were just spot on with what you were saying in terms of applications, use cases, what is it doing, how is it helping a company? That is what is going to be the most important. And right now we are at 29 useful qubits, and we're working on our 35 and 64 qubit machines. 35 is where we expect to unlock many machine learning use cases. And then 64, that's where we expect to unlock the next layer of more complex use cases. So this is what we're working on right now. To your point, Jay, it is how do we trap, control, and entangle these qubits as we grow and scale them up. But right now is the time to write these algorithms, because once the breakthroughs are there, it's going to be too late. And actually, ChatGPT should remind us of that. A lot of people are like, "Oh my God, what happened?" Almost you could call it a ChatGPT moment for their business. While when for me, I didn't think it was surprising at all. I was at NVIDIA for 7 years, and I was seeing how companies were innovating and so many incredible things with the technology, but many others were just sitting on the sideline waiting for the killer app. And when the killer app comes, it's actually too late because your competitors are there before you. So what I would say is now's the time to experiment, to build the algorithms so that when the computers are large enough, you're ready to actually take advantage of them.
Great. Bob, you want to add anything to that?
The only thing I'd add is what we're looking at now is there's two issues that I consider to be critical towards moving forward in quantum computing development writ large. The first one is noise. Quantum, you don't look around and, oh, in that corner over there, there's a couple of entangled qubits. Isn't that neat? It is very fragile and very difficult to establish this issue of superposition and entanglement. It's a very fragile environment, and you have to protect those qubits and nurture them and keep them away from things like electromagnetic fields and cosmic rays and temperatures that cause problems, thermal meshing about. So quantum qubits are inherently noisy. They live in this environment they're not really happy with. And so when you run a calculation, it's not like a regular classical computer where you put a 1 in and most likely that 1 stays a 1 until you read it out at some point. And there's some error correction involved, but not really. It's not that bad. In the quantum realm, those errors are pernicious. You introduce errors when you read a bit in. You introduce errors when you run it through a logic gate, be it something as trivial as a NOT gate in some sense. You get errors when you read out of what goes of when you're finished the calculation. So you don't run a quantum calculation. You run a number of shots, they're called, and you get a histogram of your answers. So noise is a pernicious problem, and there's so many different ways and so much innovation addressing the issue of noise. How do we deal with a system that in some senses is by design inherently noisy? How do I deal with that? So that's something that I look for. The other one is scalability. We talk about the holy grail, if you will, of 1 million qubits. I don't believe people are targeting a single chip that's going to be a million qubit processor. What we're going to do in the quantum realm from the QC architectural perspective is what we do in the classical world, which is clustered processors.
Right.
We take a number of processors and we allow them to communicate, to work in parallel, to attack a single
Mhm.
job. The thing with quantum is sending a signal from one quantum chip to another quantum chip is a non-trivial task, because that whole issue of staying within the quantum realm when you're communicating is still a very difficult problem to solve. If you want to communicate, but you're going to do it over a classical network, you lose what I call all the quantum goodness. So there's a problem there. You want to be able to scale your processors by figuring out ways to build a quantum computer that allows your quantum processors to communicate with each other over a quantum network. And that issue of scalability, in my mind, is probably one of the next big issues facing quantum computing suppliers. It's moving from the quantum chip to a quantum network, because that's what drives scalability. So I look for noise, I look for scalability, and those are the two things that make quantum a much more bulletproof and effective and widely applicable architecture. Move from the mentality of a quantum chip to a quantum processor or a quantum multiprocessor is really, I think, the next big challenge facing this sector.
Bob, I'm so glad you brought up noise, and that's a very important point. We also should probably tell our listeners that these quantum computing calculations are, their very nature of them is probabilistic calculations, which is incredibly useful for many real world problems. But its probabilistic nature combined with noise means you need to have many, many more qubits in some cases to have a subset of those that are useful, effective qubits that you can trust. Rima, before you talked about useful qubits, is that what you were referring to? The need to have many more qubits to deal with noise so that you would have a certain number that you could count on for being useful in terms of providing an accurate answer?
So actually, I think useful qubits is the right measurement to actually look at, but with ion trapped machines, you don't need so many. If you go with error correction, usually we are estimating 13 to 1, while if you look at superconducting, it's thousands.
Yeah, right.
So it's just, you have to look at the modality. But what companies are doing today, in the meantime, as we are in this NISQ era of noisy quantum computers, is we're using a lot of mitigation techniques. Like, so for example, on our computers, noise is not random. It's actually, we understand the noise. So because we understand the noise, we can actually use error mitigation techniques that take away, the noise that's introduced. But all the things that we've all been talking about are the things that we're working on right now. Whether it's networking different computers, or whether it's controlling the noise, and it's a very exciting time. But during this time, we're still able to find value in these smaller problems. And as we work on, perfecting the technology, the benefits are going to be just exponentially more attractive and beneficial, and truly disruptive in a good way.
Well, I think you two have done a great job of conveying the fact that the quantum physics is real, that the quantum computing technologies exist now at smaller scales, that there are known challenges that are being worked on by many companies trying different modalities to increase the quality of qubits and the connectivity of these qubits and dealing with the noise. And so the future looks bright here. So I need to bring up the question that people ask, which is, well, when these quantum computing systems really do have even more qubits and are more reliable, isn't that going to break current cryptographic schemes? And that seems to be, in addition to solving big problems, concern about computer security using classical methods seems to be one of the drivers of quantum computing, right? How close are we to seeing quantum computers get to that point at which they will be able to run the algorithms that crack our current classical computing security techniques?
In my mind, this isn't a quantum computing problem. This is a cybersecurity problem. Right now, NISQ is in the process of evaluating a number of post-quantum encryption schemes. The fundamental reality is all of our encryption schemes right now are based on a simple fact that classical computers don't do division very well. So basically, you encrypt your algorithms, you encrypt your data by basically taking a very, very large number, which is actually the product of two primes, and people can't figure out what the product is. So that's how you use those numbers effectively, and it's called public-private encryption key, and it's fine. The bottom line is that quantum has the ability to basically do that division using something called Shor's algorithm in a very effective way. So this got people terribly upset about what quantum could do. Now, the issue here, of course, is that's only one kind of encryption scheme, this public-private encryption. And so, as I said, NIST, which is the organization body that really is kind of the world's leader in encryption capabilities, has already started to evaluate those kinds of those things. So by the time quantum systems are available to break current encryption schemes, this public-private factoring thing with the big number, most of the organizations will have access to post-quantum encryption cryptography. There's two issues here that are relevant to mention. The first one is the folks that are concerned about this are concerned about the theme of gather now, decrypt later. So I am an organization, right, whether I be commercial or government, and I can't decrypt what you're sending over the wire right now, but I'm going to save it because in 14 years, I'm going to be able to read your 14-year-old mail. Is that a bad thing? If you are protecting intellectual property rights, if you're protecting confidential information, say a client base of patients, if you're a national government and you don't want other people reading your mail, that's a concern. So the idea of save now, encrypt later is legitimate one. But the key here is this isn't about quantum encryption. This is about rolling out an entirely new cybersecurity stream. I always like to say technology is not the problem, people are. When it comes to this stuff. So the changeover, what quantum is driving is requiring rolling out an entirely new encryption infrastructure to every business, every government, every commercial organization. And that's going to be the hard part, not developing post-quantum encryption algorithms. So that's my take is more, this is more of a human problem than it is a technical one, to be quite honest.
Nonetheless, Bob, there is some time scale that if people have not adopted a quantum safe encryption method for all of that data you mentioned, then there is a point in time at which quantum systems will be able to break the current methods, correct?
Well, to me, it's going to be infosec. It's going to be when these algorithms come available, are they deployed properly? We used to have an old joke because for years, when Digital, the company that went out of business, used to ship their mini computers, the default was always user ID was user, password was always password. And administrators always forgot to use that. So there were times I could go up to any DEX system in the world and log on because they forgot to do the infosec, get rid of the default passwords. And that's really what my concern is here. It's not the technology, it's how it's rolled out and introduced and deployed going forward. If people stick to the schedule, if they start today to start thinking about how they're going to really roll out the technology, I believe that the post-quantum encryption capabilities will be there long before quantum computers capable of decrypting information as on those days. That'll be fine. It's the save and decrypt later, and it's the lack of infosec security that's going to cause the two biggest problems.
We can focus on the promise and potential of quantum systems for doing game-changing problems and transformational problems, and we have methods and a clear path to solving the security issue.
I believe so. Yep.
All right. I'm going to ask you two really simple final questions. The first is, given all of this, given the promise and potential of quantum computing, and the fact that it is now not very far away and even beginning to see some initial promising results of commercial value, how can professionals and companies get engaged in quantum computing now? What do they need to hire quantum physics PhDs? Do they need to attend certain classes? What do they need to do to begin their assessment of whether quantum computing is going to be important in keeping them competitive and innovative?
I mean, from my perspective, every company is going to need to leverage quantum computing. So what to do right now is, pick a problem that has a good fit for near-term quantum and start working on it. Either hire a few people, or if you don't have the right talent, work with a quantum computing company or quantum consulting company. Build the application, start to understand the benefits on a small scale problem, so that you're ready to actually leverage it for larger scale problems. And yeah, today you do need some quantum physicists, but actually very quickly, regular software developers are learning to leverage the technology. We actually have a program where we do professional training to actually take like regular developers of AI and classical computing and train them in leveraging quantum computing. And the best way to do that is to work on a problem with a few people who actually know how to do this well and start building your skill sets. So my recommendation, jump in right now, pick the right problem, pick one with near-term value, and start building the skill sets and understanding where it can have benefit and impact in your organization.
Well, what I'll add to that, and this is quantum in some sense is so lucky, because if it wasn't for the existence of cloud access models, quantum would be much farther behind where it is now. The barriers to entry to explore quantum are so amazingly low. Contrast it with, say, 25 years ago. If you wanted to get into HPC, you had to drop $25 million to buy a Cray. You had to remodel your computer room for another 10. Then you had to hire 25 really technical, nerdy kind of guys to live down in that basement and write code. Now you can get on through a cloud access model and get a couple of 100 hours free of quantum computing. You can jump from vendor to vendor. You can, my favorite, and no disrespect, but it's off the top of my head, Rima, you can go to Rigetti, and you can go to Rigetti directly through their cloud. You can go through Azure Quantum. You can go through Google. You can go through AWS, you can go through Strangeworks, you can go through Zapata. You can pick the relationship you want to have with and with any quantum computing vendor nowadays. You can go from almost no cost, free, to I'd like to plug down $250,000 a year. I get access to your machine. I get access to your professional services, your expertise. You pick what you want. Yeah. We did it. Yeah. I mentioned earlier the survey. We wanted to go out to 300 QC early adopters, commercial vendors, commercial companies, and we scratched our head and said, how many companies are we going to have to reach out to before we get to 300? And the answer was 465, which means that 60% of the companies we spoke to, nearly at random, we assumed that they were HPC-S users. They had computational R&D capabilities. About 60% have some form of quantum computing activity going on already. People are starting to kick the tires. Their main goal is to understand what quantum computing can bring to their specific existing workloads, and they can do it at such low cost. And as I said, I can look at IonQ today, and I can go to Rigetti tomorrow. I can go to IBM, and I can see what works best for me, because so much of the software nowadays that's evolving is what we graciously call hardware agnostic. There's this whole level in the stack that says, I don't really care what you're running on. You can write the code. You can use Jupyter notebooks. You can use Python. You can use Qiskit. You can use PennyLane. You can use basically quantum computing development packages that don't require you to know too much about the hardware. You don't need a PhD in physics. What you need are software engineers. What you need are guys who wrote code for HPC, who finally got over dealing with GPUs and now are ready to look at quantum as the next accelerator. So it's the stack is evolving wonderfully, so you don't have to know it all. Just as I like to say, there is no Python programmer out there who really needs to know how a CMOS logic gate works. Same with quantum. There's no one out there writing quantum anymore today from the application level that really needs to understand how a qubit operates. If they want to take the time to optimize and write code that's really, really fast and efficient, they have the opportunity, but they don't have to. So we're seeing the stack mature and creating all sorts of opportunities at every level. So we don't need PhD physicists at every level. All we need in some cases are smart programmers, guys who have a Jupyter notebook and a couple of weeks. Jay, I know you're taking some quantum classes right now. Yeah. You're getting smart too. You're going to be one of those guys in a few years going, hey, classical, I don't need that anymore. So the ecosystem is magically evolving, and the low barriers to entry to the cloud is making that happen at every level with so much innovation and so much variety and so much options for cost, which is the key issue here.
You're absolutely right about the cloud. And to your point, that lowers the barrier to entry to everyone. Like, for example, we are on all the different clouds, in addition to offering our own cloud services. The only thing I'd say is absolutely you can program at a higher level and not need to know the details. Like, show that extra level of value. It does help to work with your vendor of choice, and for some problems get lower into the stack.
Oh, I agree completely. It's all about how much work you want to put in and how much optimization will commit.
Exactly.
I could point you to guys in government labs that spend 20 years optimizing a triple nested do loop that has 8 lines of code in it because it's worth the effort to do that.
Exactly.
And there will always be those guys. And so again, it's the spectrum. I can write stay up here, or certain companies get me all the way down to what's the shape of the pulse that controls the microwave for this particular qubit. It's options that's so innovative and offers so much opportunity.
Absolutely. Yep.
Great. Thank you for all of this. I'm going to summarize now for our listeners before I answer the final question. You've shared with our listeners that there are big problems that we cannot attack with even the biggest classical-based HPC computing systems. There is a new model of computing, quantum computing based on known quantum physics, and many companies are pursuing this and making rapid progress towards quantum computing systems that will be able to solve some of those problems that no classical computing system will either ever be able to solve or not solve in a reasonable period of time, perhaps. So it's real, it's coming, progress is being made. We're not all the way there yet, though. There are ways to get engaged, to work with vendors, to take classes, to work with consulting companies. And the time is now to do that, because imminently different countries and different companies will have access to this capability. So my final question, there's a old quote from a major computing vendor where one of their brilliant inventors of all time, we all say something that's not correct at some point, said maybe the world will never need more than 5 computers. In the quantum computing world, I know neither one of you two would say that you would think that the world is going to need many quantum computers, but I'm going to ask you, how soon do you think it will be before any vertical, before any domain, be it pharmaceutical or financial services or aerospace, has more than 5 working production quantum computing systems day in and day out?
So based on our modality and our work and what we're planning and working towards, we see it happening in 3 years. The value on small case problems today, and with where we expect to be in 3 years, having our 64 useful qubit machines that can examine 2 to the power 64 states at the same time. We expect to be able to unlock a number of important use cases for a number of industries.
3 years. Wow, that's very aggressive. I love hearing that. Bob.
Okay, I'm gonna really lean forward into this one. The first one is thank you for the TJ Watson quote, because he was exactly right. When he was standing up at IBM in New York and looking at giant machines that were consuming huge quantities of tubes, each tube with a failure rate of 1 in 1,000 hours, and once you get over 1,000 tubes, you're in trouble. There were only 5. Well, he didn't see the invention of the transistor. He didn't see the invention of the integrated circuit. And he certainly didn't see how many transistors are in a high-end NVIDIA GPU. Are we over 100? Are we in the billions?
Oh yeah, tens of billions.
Okay, so tens, if not hundreds of billions. He didn't see that, so he was right at the time. And I've heard people say, "Oh, there's not going to be that market for many quantum computers as well." Well, we don't see where the innovation's going just yet. We don't know what new breakthroughs, and you know, IonQ, forgive me, but I've said in more than one occasion, when people say which quantum modality wins, I say, you know what? Maybe the one that wins hasn't even been invented yet. Are we still in the tube stage? Are we still in the transistor stage? I don't know, but there's 10,000 engineers out there right now working like crazy to become the next Gordon Moore, then the next inventor, Shockley, whatever, pick your engineer of choice and say the world will change. So that's one. The second point, and Jason can wrap it up, Bob. The second point is we have to change the definition of what production is, because in the old days, production meant plop down $25 million, put it in the IT center, and turn the key and forget about it. I would argue that quantum computers are already in production in places like financial houses that are using them to help them make decisions. It's not a turnkey system that you put out in a warehouse in New Jersey. It's something that people are using to help them refine their algorithms, think about new opportunities, optimize some processes. And because you don't have to drop $25 million, their production system may be only costing them $20,000 or $30,000 a month running through a cloud service provider. So they don't have to pluck down the system. So let's define what we mean by production. So until we have the same definition, I'm not going to make a prediction about time, because I say under my definition, production use cases are already out there right now. They're not as traditional, but when was ever quantum a traditional kind of infrastructure? So I'm gonna change the calculus and throw out the definition.
Yeah, you're spot on. You're absolutely right. When it's bringing value, helping you make better decisions,
that's production.
That's production. So
because that means it contributes to the bottom line. It's not research. It makes money. It gives you return on investment. Yeah.
Well, great. Thank you both for this. I know we ran a little bit over today, but I just couldn't stop asking you questions. Your answers were so informative and exciting to hear. I really liked hearing the optimism from people who are day in, day out working in this field, know the challenges, but also know the opportunities and see the progress firsthand. So thank you for communicating that for all of our listeners. I hope our listeners will also tune into or attend in person, if you're in Austin, our quantum computing event on September 5th with Will Hurley, or Worley as he goes by, the CEO and founder of StrangeWorks, a company that Bob mentioned just a little bit ago in one of his responses. We're intending to make that a very large event. We'll cover things in even a little bit more detail then. There may be a quantum book signing at that. And then after that, we're going to start showing our attendees and listeners ways that they can begin to access these systems, initial training classes they may want to take, and so on. But thank you both for being here. I think you're going to get our listeners really excited about the future of quantum computing, and I greatly appreciate our conversations and everything you share with me. Thanks for joining us.
Cool. Hey, thanks. This was fascinating. I appreciate the time and great comments and good discussion.
Yeah, thank you very much for having us. This was a really enjoyable talk.
Thanks for listening to the Austin Forum Upload. You can listen to additional episodes and check out a schedule of our monthly in-person events at austinforum.org. The Upload is a production of the Austin Forum on Technology and Society, a nonprofit organization here in Austin, Texas.